Okay guys, next we have spectrum of sodium, alkali spectrum. What are the alkali elements? Those elements, first I will define alkali elements. Those elements in which there is only one valence electron is called or known as alkali elements. These elements includes hydrogen, lithium, sodium, potassium, etc. These are the elements in which there is only one electrons in the valence shells. Like hydrogen is atomic number 1, lithium is 3, sodium is 11, and potassium is 17 I think, and so on. So these elements have only one valence electron in the valence shell. For example, for hydrogen the electronic configuration is 1s1, so there is only one electron in the valence shell. For lithium we have 1s2, 2s1, so there is only one electron. For sodium we have atomic number 11, so 1s2, 2s2, 2p6 and 3s1, so there is only one electron in the valence shell. So these elements are called what we call it, the alkali elements. Alkali elements, yes. So here we will discuss the spectra of sodium only. We will discuss the spectra of sodium. And we already discussed the spectrum of hydrogen. Spectrum of hydrogen. Hydrogen. And we already know that there are 5 series in the spectrum of hydrogen, and these series are Lemon series, we have Balmer series, third one is Paschen series, fourth one is Briquet series, and the fifth one is Pfund series. And I have here these series are given here. Here we have a transition from higher energy level, like from n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, n is equal to 7, to n is equal to 1 states. Lemon series is obtained from higher energy states En to energy state for which n is equal to 1. This is Lemon series. Similarly, we have Balmer series. This series appear due to transition of electrons from higher energy level En to energy level for which n is equal to 2. And then we have Paschen series, and this Paschen series comes from the transition of electron from higher energy level En to energy level for which n is equal to 3. This n is equal to 3. And then we have Briquet series, which comes from the transition of electron from higher energy level En to energy level for which n is equal to 4. And then we have Pfund series, and this series appear due to transition of electron from higher energy level En to energy level for which n is equal to 5. So we already discussed in detail about this series, and the frequency of this spectral line in this series is given by this formula. Nu is equal to 1 over r, sorry, it's r, not 1 over r, into 1 over n1 square minus 1 over n2 square. This is the wave number. This is called wave number. And this r is, we call it Rydberg constant. By using this formula, we can calculate the frequency of each of these spectral lines. Where n1 and n2 are the principal quantum number of the energy levels. Like n1 is the principal quantum number of the energy states of the energy level where the electron make transition from n2. Like this is the principal quantum number of this higher energy state, and this is the principal quantum number of these states. N is equal to 1 for Riemann series. For Balmer series, n1 will be 2 and n2 will be 3, 4, 5, 6. For Paschen series, n1 will be 3 and n2 will be 4, 5, 6, 7. And for P-Fund series, n1 will be 5 and n2 will be 6, 7, and so on. So this is all about what we call it the hydrogen spectrum. Now, in addition to hydrogen, other elements having the simplest spectra are alkali elements, because in alkali elements there is only one electron in the valence shell. Like each alkali atoms contain one valence electron in addition to the complete subshell of electrons. Among alkali atoms, sodium is the simplest of all. So here we will discuss the sodium spectrum of sodium. Like hydrogen, there are 5 series. In sodium spectrum, there are 4 series. And these series are, I will list it here. Sodium spectrum contains 5 series. Sodium spectrum contain 5 series, and there are, one is called principal series, second one is called sharp series, third one is diffuse series, and the fourth one is fundamental series. Now this principal series is bright, it's bright and most intense. It contains bright and most intense lines. This sharp series and the diffusion series is comparatively broader lines. It has comparatively broader lines. And this fundamental series appear in the infrared region. So we will discuss why there are 5 series appear in the sodium spectrum, why principal series contain bright and most intense lines, why diffuse series contain broader lines, why this fundamental series appear in the infrared region. So for that, I will discuss another energy diagram of hydrogen atom. This is another energy diagram of hydrogen atom. The energy level diagram of hydrogen atom. As we know that the energy of nth states, electron in the nth states, is given by this relation. En is equal to minus 13.6 electron volt, minus 13.6 over n square electron volt. If I put n is equal to 2 in this equation, we get the energy of the electron in the second shell, which is minus 13.6 over 4, which is minus 3.4 electron volts. And this minus 3.4 electron volt, I started from 0. Here we have 1, 2, 3, 4, 5, 6 minus in the negative direction. So this minus 3.4 appears somewhere here. So this is the energy level for n is equal to 2. For n is equal to 3, if I put n is equal to 3 in this equation, I have minus 13.6 over 9 because we have n square. So 3 square is 9. So from this we get the energy of this third energy level with n is equal to 3 is minus 1.5 electron volt. And 1.5 electron volt is given here. This is for n is equal to 3. Now for n is equal to 4, we have minus 0.9 electron volt. And 0.9 electron volt is somewhere here. Minus 0.9 electron volt. And then we have n is equal to 5, which is minus 0.5 electron volt, which is minus 0.5 is here. This is minus 0.5. This is minus 0.9. And this is minus 3.4. And this is minus 0.4 for n is equal to 6. As we see that, as we move to higher energy level, the spacing between two consecutive energy levels, it decreases. So the energy difference also decreases here. Like the first energy level is somewhere down here. The second is here, so there is a large space. The third one is comparatively closer, which is a smaller space. The fourth one is more closer. The fifth one is more and more closer, and the sixth one is more and more closer. So the energy of higher energy states, or the energy difference decreases as we move away from the nucleus. If I plot this diagram in circular shape, we have, this is the nucleus, this is K shell, this is L, this is M, this is, we have N, and so on. And finally at infinity, these energy levels overlap each other, because as we move away from the nucleus, the energy of the shell, they are decreasing, or the difference between the energy of two consecutive energy levels decreases. So this is the energy level diagram of hydrogen atom. Now we have sodium. For sodium, we have the electronic configuration is, is 11. Its atomic number is 11 and its electronic configuration is 1s2, 2s2, 2p6, 3s1. Now these are the core shell. They are completely filled with electrons. So they are not participating in any of the optical or electronic properties of these sodium atoms. So we have this 3s suborbit, which is important. This is the valence shell. So we have to discuss this one. Now the valence electron is in the 3s suborbit, and above 3s orbit we have 3p, we have 3d, and we have 4s, 4p, 4d, 4f, and so on. So we can say that above 3s orbital, there are suborbitals, like we have 4s there above 3s, we have 5s, we have 6s, we have 7s, and so on. Similarly, we have 3p, sorry, we have, because after this we have 3p, we have 4p, we have 5p, and so on. And similarly, we have 3d, we have 4d, we have 5d, and so on. And similarly, we have 4f, we have 5f, we have 6f, and so on. So these suborbitals occur above 3s. Now I will plot these suborbitals in this hydrogen spectrum, energy level diagram of this hydrogen spectrum. And here I have another diagram. Now 3s appears here. So there is a big space between 3s and 4s. So this is 4s now. Then we have 5s, 6s, and so on. 4s is somewhere here, 5s is somewhere here, 6s is somewhere here. Now after 3s, we have 3p. 3p means 3p, 4p, 5p, 6p. So 3p is above 3s. So 3p is here. Then we have 4p, 5p, 6p. These dotted lines, they represent the energy diagram, energy of hydrogen atoms. Phi n is equal to 2, this is phi n is equal to 3, this is phi n is equal to 4, this is phi n is equal to 5, this is phi n is equal to 6. This is same like this one. So n is equal to 2 appear at 3.4 electron volt in hydrogen atom. This appear at 1.5, minus 1.5 electron volt, and then we have 0.9 electron volt, then we have 0.5, 0.4, and so on. So these dotted lines, they represent the energy level of hydrogen atoms. And these energy levels, I have this 3s for the sodium, then we have 4s, 5s, 6s in this way. Now 3s and 4s, there is a big space, and then the space is decreasing as we move away. Next we have 3p, so 3p is higher than 3s, so 3p appear here. Then we have 4p, 5p, 6p. After 3p, if I look at here, 3s, 3p, then we have 3d. So 3d is here. 3d will be higher than 3p. So then we have 3d, 4d, 5d, and 6d. And then we have 4f, 5f, 6f. Because 4f comes after 3d. If you look at here, 4f comes after 4d, 4p, and 3d. So 4p, 4f, and 4s is there. Now these are the energy levels in sodium atoms. Now the transition takes place only if the following selection rules were followed. And the selection rules are I will discuss the selection rules in the next video. I think the length of this video is almost 20 minutes. Thank you.